So this is type B. Then type C we have already discussed yesterday, doubly fed induction generator with gearbox and then back-to-back converter of 1/3 capacity on the rotor side, right? This we have discussed. And then type D is the permanent magnet PMSG machines, and you don't have to use gearbox as we were discussing, but you have to have full size converter, back-to-back full size converter connected on the stator of the machine, and it gives very good performance, this type D, but it is costly. But you can have full fault right through capability, low voltage, high voltage right through capabilities, because it is totally decoupled because of the back-to-back full size converters here. So we already know the cost, performance, what you need in your wind farm, but as far as Quebec is concerned, my home province in Canada, they are using this type C type, using doubly fed induction generator. But as we discussed yesterday, the technology for off-grid system, no, not off-grid, C, what you call it, offshore wind turbines for large generators, 10 megawatt, 13 megawatt, 14, 15, even they are trying to develop 20 megawatt PMSG machines. Okay, so those are PMSG machines for offshore applications. Okay, now coming to our point, hybrid standalone power electronic systems. Okay, this is the example of AC standalone microgrid. So you have AC microgrid here. Okay, so here you have diesel generator, fixed speed diesel generator you have. Okay, so voltage and frequency remains constant here on the AC bus. Then you have wind turbine, squirrel cage induction generator, for example, if you have, but if you, with this machine, if you want to have MPPT, you have to have full size back-to-back converters and inverters. Okay, so this, now you can use hydro turbine with squirrel cage induction generator, right? This is PV photovoltaic DC to DC converter to have MPPT on PV, and then you need DC to AC inverter to connect it to the AC bus with having constant voltage and frequency. You can have battery bank DC to DC converter for charging, discharging battery bank, and then you have inverter here. So if DC loads are there, you can connect it here. If you have AC loads, you can connect it to the AC bus. Okay. So this is just an example of AC standalone. Similarly, you can see the DC standalone microgrid. So this is DC standalone microgrid. Standalone means it is not connected to the grid, right? Standalone means it is not connected to the grid. So our topic is hybrid standalone system. So that is why I am emphasizing on off-grid system which is not connected to the grid. So here this is DC bus. So you can have PV here and DC to DC converter. See, you don't have to have an inverter here. So you can save money, right? If you have this squirrel cage induction generator, you can have AC to DC converter to connect it to the DC bus. Then you have AC load and everything, battery bank, you see DC to DC converter. So this is an example of DC standalone microgrid. Then there are lot of hybrid AC-DC standalone microgrids. So you have AC bus as well as you have DC bus. The generators and load which are DC in nature, they will be connected to the DC bus. And the generator and load which are AC in nature, they will be connected to the AC bus. And it means between AC and DC bus, you have a bi-directional converter. So power flow can take in any direction, either in this direction or in this direction, depending on the situation. So that's how you can save a lot of money. So if you see the Comparison between AC and DC microgrid. Advantage of AC standalone microgrid. Utilizing existing AC grid technology and off-the-shelf product. And well-established protection and standard, because AC grid is there for last more than 100 years, right? Disadvantage of AC standalone microgrid. Every time you have to do synchronization, stability problem, need for reactive power, power quality problem, those things are there. So these are the disadvantages of AC standalone microgrid. If you see the advantage of DC standalone microgrid, all disadvantages of AC standalone microgrids are not present, like synchronization. You don't have to do synchronization with DC grid, right? You are not worried about the reactive power compensation and those things. Most environmental friendly distributed generation such as photovoltaic, fuel cells, variable speed wind power system generate DC power, and most digital loads require DC power. Okay, it can eliminate AC, DC, DC, AC conversions. And in terms of, it has the advantage over in terms of efficiency, because less conversion, because of, and then cost and size. And there are disadvantages of DC standalone microgrid, that you have to see the protection circuit and other things for DC voltage. Same way, there are so many advantages of hybrid. So that's why a lot of work is going on, hybrid AC DC standalone microgrid, because if you have AC load or AC generator, you connect to the AC grid. If you have DC load or DC generator or batteries and those things, or PV, you connect to the DC bus, and in between the two you have bi-directional converter. So you can save lot of money by saving lot of power conversion. So it is more efficient. But however, there are disadvantages of hybrid AC, because energy management, control, operation are more complicated in the hybrid system. There are so many topologies. Okay, few years back we were doing the survey of those. So as I told you, we found more than 60 topologies which are already being used by different engineers around the world. So these are the topologies based on fixed speed diesel generators and variable speed wind turbine coupled to doubly fed induction. So you see diesel generator using squirrel cage induction generator, diesel generator using PMSG, diesel generator using synchronous reluctance machine, diesel generator using classical synchronous generators, and here you can see this is the wind turbine defig machine. On the rotor side you have AC to DC converter, and then this is a DC bus. See, this is the AC bus and this is the DC bus. On the DC bus you have battery bank, maybe a dump load and a capacitor, and here you have DC to AC converter. So fixed voltage and frequency you connect it to the AC bus. So the power flowing from stator to this, or it can go through this also. Here you have a battery bank and the dump load. Again, topologies based on fixed speed diesel generator, variable speed wind turbine coupled to squirrel cage induction generator. So diesel generator, see different type of machines you can use, and with the wind turbine you can use squirrel cage induction generator, and then here you need full size back-to-back converter, while in defig you have 1/3 size of this thing. Okay, but with squirrel cage, because on rotor side there is no winding, right? So on stator only you can connect back-to-back full size converters, and this is the DC bus where you have battery bank and dump load, etc. Topologies based on fixed speed diesel generator, variable speed wind turbine coupled to synchronous generator. So see different types of machine used with diesel generators, and here you have a wind turbine and classical synchronous generator with automatic voltage regulator and exciter. Okay, and the stator is connected to the full size back-to-back converters. Okay, so this may cost a little bit more. First of all, this machine is costly, and then you have full size back-to-back converter, and this is the DC bus where you are putting battery bank and the dump load. Topology is based on fixed speed diesel generator, variable speed wind turbine coupled to PMSG. So you see diesel generator connected to different machines as a generator connected to the AC bus. You will have constant voltage and frequency here. But if you see this wind turbine, this is PMSG, and stator is connected to the full size back-to-back converters. So this is a little bit costly thing. Topology is based on fixed speed diesel generator, variable speed wind turbine coupled to synchronous reluctance generator. So you can see different types of machines are here for diesel generator, but within wind turbine you have synchronous reluctance generator, which is like squirrel cage induction generator, but it is more efficient, considered to be more efficient and robust. So in the stator you have full size back-to-back converters here. Topology is based on variable speed diesel generator, see, and variable speed wind turbine coupled to diffig. Now you have diesel generator with different kinds of machine, but for example, this is diffig, wind turbine and double-fed induction generator. Rotor side, you have 1/3 capacity of this converter, AC to DC converter. This is DC bus. And on this DC bus, you are bringing your diesel generator output. So this is producing AC, but you have AC to DC converter. You are bringing this voltage power on the DC bus of this. So the power will flow like this to the AC bus. So it means the size of this inverter will increase because it has to take care of the power coming from diesel generator also. But still it is very efficient because it is a variable speed diesel generator. Okay, so if the load is less, you can have a less speed, but the efficiency of diesel generator will be more. Okay, and you see a very interesting topology here. I think it was developed in Peru. So diesel engine with doubly fed induction generator. Stator is directly connected to the AC bus, and rotor side you have AC to DC converter, and which is coming to the DC bus, and this is again doubly fed induction generator for wind turbine. Stator is directly connected to the AC bus. Rotor side you have AC to DC converter with 1/3 capacity, but the size of this inverter will increase because power has to flow like this. Okay. Topology is based on fixed speed diesel generator, variable speed wind turbine coupled to diffig and solar PV array. So you see, this is wind turbine, doubly fed induction generator. Rotor side you have AC to DC converter of 1/3 capacity. Then this is the DC bus where you have battery bank and dump load, and then the size of this inverter will increase because PV power is also coming on DC. So this power will be transferred here. So PV power, this is DC to DC converter for MPPT, and this power is coming to the DC bus. So size of this inverter will increase because this power plus this power is going, and this is fixed speed diesel generators. Topology is based on variable speed diesel generator, variable speed wind turbine coupled to diffig and solar. So you see, again suppose we say wind turbine, the fed induction generator, rotor side, 1/3 capacity, AC to DC converter, but then on this DC bus, diesel engine output is coming and also PV output is coming on the DC bus. So the size of this inverter will increase to take care of this power and this power also. Okay, so you are having variable speed diesel generator here. And again the same thing, suppose you have defig machine here for wind turbine, rotor side 1/3 capacity AC to DC converter, but diesel engine you are having doubly fed induction generator, stator is connected here and rotor side 1/3 capacity, but this power is coming to the DC bus. Moreover, power from PV is also coming to the DC bus. The size of this inverter will increase. Hybrid wind diesel PV fuel cell system based on variable speed generator. Okay, so you see this is AC bus, this is DC bus, and on the DC bus you have here defig, here PMSG, here synchronous generator, here is PM build DC, squirrel cage induction generator, synchronous reluctance generator. So this defig rotor is connected to this 1/3 capacity of this machine. Then you have a fuel cell system also on the DC bus. This is DC bus and this is AC bus. So fuel cell is connected to the DC bus, battery bank is there, and then PV is also connected to the DC bus, and diesel generator using this machine is connected to the DC bus. So this is the interfacing inverter between DC and AC bus, and power can flow either in this direction or in this direction. And this is hybrid wind diesel PV fuel cell micro hydro system. So here you have added a micro hydro. Sometimes what happens, there is a small community, and in the back of a small community there is a small river going, because generally what happens even in India, in Canada also it is like this, that those communities are generally near a small river, right, so that you don't have a water problem. So in the north of Canada also there are so many communities just near a small river, although that river freezes during the winter time, but still maybe 1 feet or 2 feet frozen, but under it the water is still flowing. Okay, so you can still use the this micro hydro turbine. Okay, so that's why micro hydro turbine is there. Otherwise rest of the things are same. This is wind turbine with doubly fed induction generator, rotor connected to this AC to DC converter. This is the DC bus, this is the AC bus, and then fuel cell and battery bank and PV and variable speed diesel generator. But these are different machines, so little difference in topologies. So coming to the conclusion, electric power supply to many isolated regions of north of Canada is presently being managed by diesel generators. You cannot avoid the diesel generators. Efforts are being made to integrate renewable energy sources to reduce fuel consumption. Otherwise the cost is very high, like I told you 43 cents or 90 cents per kilowatt hour. Standalone wind energy conversion system with battery are suitable alternative for small and medium power demand. To increase the efficiency of diesel engines, variable speed diesel engines are now available in the market. But further research work is being done to promote various high efficiency topologies of electrical generator. Researchers are attempting around the world to develop cheaper, lightweight, more efficient electrical machines. As I told you, synchronous reluctance machine, and still work is going on to improve the efficiency and the performance, and to reduce the dependence on permanent magnet, because 90% of the market of permanent magnet is occupied by China. So you are depending on basically on China. In future, with the development of proper technology, DC microgrid may be a more logical solution. And in the next lecture, I will tell you, because so much work is going on data centers. Data centers is the thing of the future, and still now in India also at many places, They are installing big size data centers, and they consume lot of power. And this is what the topic of discussion I attended in July this year, 2025, PES general meeting in Austin. And the first day panel session was on this thing, that the four CEOs of the big companies, they were discussing about this thing, that data center will consume lot of energy. We need lot of energy for data centers. Many combinations of hybrid renewable energy systems are being researched, developed with promising results, depending on the availability of natural resources and the budget. So if you don't have budget, you cannot do anything. You can have big plans, but you don't have money. What will you do? Moreover, you have to see what are the natural resources available nearby. Like in India, situation is different. North of Canada situation is different, temperature is different. In India, all the time you have good weather. In Canada, everything freezes in the winter. US, there is a situation different. China, there is a different. So different type of batteries perhaps. Whatever batteries you are, lead acid batteries you are using, perhaps during the winter time in Canada, you cannot use those batteries. Otherwise, you have to have a heated room for the batteries. So there are so many factors. Every part of the world, they have different solar radiations, wind profile. So depending on that solar radiation and wind profile, your topology will change, right? So you have to see how much wind is there in particular region, how much solar irradiations are there. So the topology will change based on this thing. So as Professor Madhusudan Singh has entered here, so I am finishing my lecture now. Thank you very much. So this is a tea time now. Yeah.
We can go for tea. Now they are mostly in examination mode.
Yeah.
So they are trying to look back what was done for last 5 days.
So Professor Madhusudan Singh, I just discussed different topologies here. यहाँ पे hybrid standalone, they are not connected to the grid. Hybrid standalone renewable energy system. So I discussed many topologies here. So just to give the basic idea of what is going on around the world, and I discussed.
In Canada, what is the wind speed, average wind speed?
Yeah, so this is what I discussed, and maybe I will give you the brief idea in my next lecture also. See, this is the wind profile.
7-8 meters per
Average wind profile in Canada. In the north of Canada, lot of wind. So if you see average wind power, so in this region, you have around 1000 watt per meter square of power generation in Canada. And even other part of the world, 500, 600 watt per meter square of power generation due to the wind.
in Quebec area, it is
Yeah, this is the Quebec area. So in the Quebec area, in the north of Quebec, it is very good. North of Quebec, it is 500, 600 watt per meter square. But,
it comes in north, sir, or which area?
pardon?
Montreal is north.
No, in the south. All big cities in Canada, in the south of Canada, near the US border. Like Vancouver, Montreal, Toronto, they are just near to the US border in the south. So most of the population in Canada.
So we have, I think, one more lecture is left.
Yeah, see, this is the south of Canada. So all the grids are there. But in the north of Canada, there are so many communities which are not connected to the grid. So this is what I was talking about this. They need diesel generators. They cannot avoid the use of diesel generator. So a lot of work is going on to integrate renewable energy with diesel generators to reduce the overall cost of the diesel generator. Otherwise, it is very costly. So I told that I am in Montreal. My cost of electricity, I pay to Hydro-Quebec 7 cents, 8 cents per kilowatt hour. But in the north communities, it costs 42, north of Quebec, 42, 43 cents per kilowatt hour. And in other part of Canada, it may reach even 90 cents per kilowatt hour. So this is very costly. But
Maybe the hydropower in Quebec, that's why it is cheaper or?
yeah. So we have 100% renewable energy, non-polluting power in Quebec. 90% is hydropower, around 40,000 megawatt, and 4,000 megawatt of wind energy in Quebec. But we don't have much this solar. And I told yesterday, I was telling a very good, interesting story about solar, that I wanted to install a solar panel at the roof of my house. And then I came to know that I will not be able to recover my money for next 28 years.
Oh, that is the
Because the electricity is so cheap in Quebec, you cannot recover your money. While in other places in California and New Jersey, the price of electricity is high, so it is faster to buy. Some people were saying in 2-3 years, right? You were telling that in Rajasthan you are able to recover your money in 2-3 years. So, but this is not the case in. Okay, so now this is the final lecture of my presentation. I want to thank DTU for giving me this opportunity. Professor Madhusudan and everybody are so helpful. Thank you very much, everybody.
thank
For,
you, sir, that
and especially I find so nice that you have such a nice faculty. Everybody was sitting there talking informally. I really find it very interesting. Thank you very much for letting me know this thing. Okay, so in this lecture, I thought it is good idea to give some what is this situation, electrical energy situation and microgrid projects in Canada. So in this presentation, I will give power sector overview in Canada, then independent electricity system operator. They have some forecast for Canada. Then installed wind and solar capacities in Canada, although we discussed a little bit in my earlier lecture. Then wind profile in Canada, solar profile radiations, this we have already discussed. And then Canada diesel dependent communities, clean energy for rural and remote communities program has been started by government of Canada a few years back. Then microgrid solution, climate change situation in Canada, some supported grid connected and off grid micro projects. I will give you some idea, and then we did some projects. I will discuss about those things. So as you can see here, %79% of Canada's electricity is generated from non-polluting sources. 79%. How those 79? 55% is hydropower, 15% is nuclear power, so 70%, and then 9% is solar and wind power. So this is how 79% is from non-polluting sources. Then we have fossil fuel, 21%. So you see here in this diagram, this is 55% hydro energy, then 9% is wind and solar, then nuclear energy 15%, then fossil fuel, gas, etc. around 16%, and around 5% coal. So this is how it comes 100%. So 21%, like 16% gas and other fossil fuel, and then 5% coal. So this is what is actually the Canada power sector. If you see total terawatt hour, it is around 630 terawatt hour of total power, and then emission from sources, polluting gases, they are slowly being reduced from to generate the electricity. So if you see Canada Independent Electricity System Operator electricity demand forecast. So you see, if you see the industrial sector, it's around 42 terawatt hour of industrial sector electricity demand presently, and in next 25 years it will be around 70 terawatt hour. So this is how it will increase in the next 25 years. If you see the commercial sector, it's also around 42, 43 terawatt hour, and the next 25 years it will be also around 70 terawatt hour. Residential sector, as the population is slowly increasing, so the residential demand will also slowly increase. Then the transportation sector. See, presently we have around 1 or 2 terawatt hour in transportation sector, but in next 25 years it may reach around 45 terawatt hour because of electric vehicles and those things, right? Because big work is going on in this direction. Then the data centers, presently it is around 1 or 2 terawatt hour, but in the next 25 years it may be around 15 terawatt hour. So this is what I was telling earlier in the earlier lecture, that data center is a big power consumptions, and I was there in Austin PES general meeting in July 2025, and the opening panel session discussion, there were 4 CEOs of big companies, and everybody was emphasizing on this thing that data center will be a very big consumption. They will need a lot of consumption of electricity. It is only in Canada that from 1 or 2 terawatt hour, it will go to 15 terawatt hour. But US is around 10 times bigger than Canada, and they have lot of development. So there will be lot of, even in India, I see lot of data centers are being, so they will be consuming lot of electricity, but I think India is already ready for that, to have the renewable energy integration, providing power to those things. Then agriculture sector, it is almost constant. So this is the forecast. Now, if you see installed wind and solar capacity in Canada, so wind and solar together is 24 gigawatt, 18 gigawatt is wind, and around 4 plus 2, around 6 gigawatt of solar energy. Now you will say, what is this? This is nothing, right? 24 gigawatt and then 18 wind and 6 solar. What are we talking about? But yeah, so this is what you have to see. In India, every year a new Canada is born. So this is the population situation. Every year in India, a new Canada is born. So you cannot compare the two things, right? So this is what it is. But if you see from other point of view, as I always telling that in my province, home province, Quebec, we have 100% electricity, renewable energy. While in India also a lot of work is going on, like how much, around 75 gigawatt perhaps wind, and then more than 130 gigawatt of solar or something. So a lot of work, so much work, incentives given by the government, a lot of work is going on in India. So this is what is the situation in Canada. So in Canada we have what, 79% is non-polluting sources. I think we have around 150,000 megawatt of power generation total in Canada, out of which around 79% is non-polluting. While in India, how much? 450,000 gigawatts, no, 450,000 megawatt or something, and around 55% I think is renewable presently. This is the situation in India.
Well, Canada installed capacity is 150 gigawatt.
Yeah, something 145,000 megawatt to 150,000 megawatt, something like that. 145 gigawatt to 150 gigawatt, something. But in
around, I think 485 gigawatt.
Yeah, 485 gigawatt in India, and I think around 50% is renewable energy.
In India, we do not have 50%. I think
Yeah.
30%.
How much?
20 to 30%.
No, you have, I think, more than 200 gigawatt is renewable energy. Wind is more than 75,000 megawatt, 75 gigawatt, and solar is also around 130 gigawatt. So more than 200 gigawatt in India you have renewable, out of 485 you are saying. But I saw somewhere that is around 51% in India is renewable energy now, perhaps. Because then you have nuclear also, and perhaps that's how perhaps they are calculating. Okay, so this is, we have already seen the wind profile in Canada. North of Canada, wind profile is fairly good, and the power generation we have already discussed in my last lecture. And solar radiations also we have already seen. In the south of Canada, we have very good potential of solar energy, more than 1500 kilowatt hour per kilowatt of installation per year. So this is how we define. And in this is the province of Quebec. In Quebec also, South Quebec, you see very good potential. Even in the north of Quebec and the north of Canada, it is not that bad. You have around more than 1000 kilowatt hour per kilowatt of potential. So this is what we were talking about. Canada diesel dependent communities. So this is what it is about the diesel dependent communities. So in the north of Canada, you can see all those communities, they are totally dependent on diesel. They are not connected to the grid. In the south part, almost it is connected to the grid. But there are 250 communities in total in Canada which are not connected to the grid. So they are totally 100% dependent on diesel generators. So this is the situation, and as I have told you, this it is very costly. Diesel consumption, diesel cost, as I told you, in Montreal I am paying 7 cents, 8 cents per kilowatt hour, but in the north some communities are paying 43 cents per kilowatt hour. In other part of Canada, even 90 cents per kilowatt hour electricity cost is there, because the diesel has to be airlifted in many communities. So you see in this table, perhaps you cannot see, it is very small, but there are some communities, the diesel has to be airlifted. So that is why cost is high there for diesel, right? Long distance barge is like a big boat, flat bottom boat you can see. So they transport many times diesel through this. So that's why bulk price of diesel fuel in some communities $2.36 per liter. So this is very costly. In some other communities, like see, sometime winter roads are there. Winter roads means lake is there or river is there. In winter time it freezes, so you can drive on the lake or river, so you can deliver. Otherwise there are not proper roads there to deliver to those communities. Yeah, winter road. Winter road is the same thing, like there's a lake which is frozen, and then you drive maybe 1 feet or 2 feet of solid ice, and there you can drive your car or truck on that road. Although it is risky, but it is done. It is the normal way during winter time. Then you see some are highway connected, so it is cheaper there. Greenhouse gas emissions for electricity, you see, this is for different, like transport, and this is transport thing, orange, and then green for electricity. So for generation of electricity, slowly the consumption of diesel is reducing, and you see the greenhouse gas emission for generating the electricity is becoming less and less. Now, since we are talking about remote communities for electricity and heat generation, this is for electricity generation for remote communities. 79% is dependent on diesel, 19% solar, wind, hydro, those things, and then other fossil fuel like gas and coal and those things. So this is for electricity generation. Now for heat generation also, 69% are dependent on diesel, 10% other fossil fuel, and wood stove 20%, and biomass, and that is only 1%. So this is the situation. Now the efforts are being made to reduce the diesel consumption. Okay, and there are 4 pathways through which the diesel is used less and less. So one is energy efficiency, another is renewable electricity, renewable heat, and grid connection. So these are 4 ways how the diesel is less and use. Pathways to diesel reduction in remote communities. Diesel equivalent use, suppose in 2015 this much diesel equivalent was used, but over the years it is being reduced because of these 4: energy efficiency, because energy efficiency of like generators or machines or equipment. So government is emphasizing, if you have a better efficiency, then there will be less consumption. and then renewable energy, these things are there. So in 2020, 4 pathways collectively contributed to 12.3 million liters of diesel